Hello everyone, welcome back. We were halfway through the derivation of ratios of post heating in the tube versus before heating, ratios of 2:1 for various quantities. Today we will pick up temperature ratio. So, we will start with this expression rho 2 by rho 1. This is of course equal to, from P equal to rho RT, I can write rho 2 as P2 by T2. Okay, and it comes out to be this relation. Now, we already had an expression for P2 by P1, okay, but we want an expression for T2 by T1. I do not know rho 2 by rho 1 yet. So, I want to rewrite this rho 2 by rho 1 in terms of U2 by U1, which will be, we know from mass equation, it will be U1 by U2. Now, this can be written in terms of T2 and T1 and M1 and M2, right. I will just write this as M1 by M2 square root of T1 by T2. Mach number times the speed of sound is your velocity. Okay. So, now I look at this expression and this expression. I already had an expression for P2 by P1, which is same as your shock relations. This relation we already had. So, I have P2 by P1 in terms of M1 and M2, and the remaining things, if I look at it, if I connect these two, only T2 by T1 and M2 and M1 are present. So, I can rewrite this and get to an expression for T2 by T1, and that will be P2 by P1 multiplied by M2 by M1 whole square. Okay, the square comes from the square root and this reciprocal. Okay, you will get to the square root anyway. Okay, so that expression comes out to be M2 square by M1 square 1 plus gamma M1 square by 1 plus gamma M2 square. Okay. This is an expression for T2 by T1. Now, I will again use this expression and substitute one of them to be m equal to 1, and I will get an expression for T by T star. This happens to be 1 plus gamma divided by 1 plus gamma m square whole square times m square. Another relation which is typically listed in tables. Of course, you know that this is already listed in tables. I already talked about this. In terms of P by P star, it will be listed. Okay. So, of course, from here immediately I can go back and use this relation rho 2 by rho 1 in terms of either I can use this, or I can use directly this M1 by M2 times square root of T1 by T2 from here, and I will get to rho 2 by rho 1. I will just write the final expression for that. That is simple enough for you to figure out. Rho 2 by rho 1 okay. This is what you will get, and of course, you can write a rho by rho star, and by the way, this is also equal to U2 by U1, the other way, U1 by U2, sorry, U1 by U2, that is how it will be. Okay. So, now I can write my rho by rho star, which is also equal to U star by U, is given by 1 plus gamma m square divided by 1 plus gamma times m square. This will be a relation. Okay. Another quantity which is listed in your tables. Typically, they will list one of these two, they will never list both of these, useless, right, you know they are equal, okay, or one is the reciprocal of the other. Okay. So, the next quantity we want to do is delta S, delta S by Cp. Okay. This is equal to log of Oh, now I have to be a little more careful. I will write this more specifically as S minus S star divided by Cp. Okay, I want to define what is state 1, what is state 2, so that now when I write my expression it will be easier to think about. This is equal to log of T by T star minus R by Cp times log of P by P star. This is just coming from delta S is equal to Cp log T2 by T1 minus R log P2 by P1. Okay, that is how you get to it. I just divided by Cp, so I just put it as divided by Cp. Of course, R by Cp you can write it as gamma minus 1 by gamma, and you can substitute for P by P star and T by T star in terms of Mach number, and you will get to a final relation log of m square 1 plus gamma divided by 1 plus gamma m square to the power gamma plus 1 by gamma. Okay, that will just come out of your expression because there is a half plus gamma minus 1 by 2, gamma minus 1 by gamma you will get S minus S star divided by Cp. This is the other relation you have. Right. Now we know that you cannot have infinite amount of heat added to my system. How do I know that? If I start from a Mach number any m1, does not matter subsonic or supersonic, I can at most go to m equal to 1 finally if I heat it. So I want to find how much is the maximum amount of heat that can be added to the system. Okay. So if I want to find that, how will I find that? It is not very difficult to find at all. All I have to do is T naught star minus T naught, this times Cp, this will be my maximum heat, right. This is our basic heat equation we started with. Okay. This is going to be equal to your Qmax. Actually I used a small q, I believe. I will stick to that convention as of now. Qmax per unit mass basis. Okay. Now I will write this expression in terms of Qmax normalized with Cpt, and that expression in terms of Mach number comes out to be this. Of course, it is very simple to derive, so I did not do it. We already have expression for T naught star by T naught. Okay, and from there you can get T naught by T multiplied with that, and you will get to this relation. Not very difficult to derive, I just did not do it. Okay. Now, once we have all these, we have to understand the properties of these functions. So, we will go to the screen there. Oops. Okay. First, I am plotting T naught by T naught star. Okay, you should understand here that T naught star is always greater than T naught for any Mach number. At most it is equal to 1, T naught equal to T naught star for m equal to 1. Okay. So, what I am plotting here, T naught star is the final thing that is possible if I heat it, okay, and T naught is the actual value. If I look at the solid lines, those are T naught divided by T naught star. Okay. If I look at it, we know that if I am heating the gas, I am going towards m equal to 1. So, I am going to start somewhere far away and go towards m equal to 1. If I think about a small change in Mach number from 1 on either side, we can see that the slope is much steeper on the subsonic side than on the supersonic side. The way to think about it, let us just pick one of the curves here. We do not want to look at all the gamma values, let us just say pick red because that is very prominent here currently. I will just pick the red one, red happens to be gamma equal to 1.67. Okay. I will just pick the red one. I am thinking about if I go from 1 to 0.5, I am dropping a lot in my T naught, which actually means that if I am adding heat, I can add a lot of heat, or my delta T naught will be very high from m equal to 0.5 to 1 than from m equal to 1.5 to 1. Okay. This is in a way similar to what we expected in our friction flows, where we said if I had a subsonic flow, it can handle a lot more heating, a lot more friction. In this case, it can handle a lot more heating. Okay, it is taking the similar approach. This is the reason why the supersonic flow will suddenly take a subsonic path by going through a shock, and then it can handle a little more heat, okay, and it can still try and manage to get m equal to 1 at the exit without worrying about changing the flow completely. That is a possibility. This is very similar to what we did in friction flows. So, I am just telling you directly that there could be a shock sitting in your flow, and that can jump across to the other path and come from there to the subsonic solution. Okay. Now, we will look at the other curve, P naught by P naught star. We know that P naught will always decrease because of adding heat. Why? P naught is related to my entropy. Okay. P naught is going to drop and it is going to come down to P naught star, and of course I know that as I am heating I am going to come down this way, this particular path. By the way, if I am cooling, it can go the other direction. Okay, always remember that we are thinking about heating only as of now. If I cool, everything goes the opposite direction. I can remove a lot of heat from m equal to 1 flow if I go subsonic path, if I am cooling. Okay. Anyways, so now we will just think about P naught curve. We find that if it is supersonic flow, there is a huge drop in P naught, while subsonic flow there is lesser drop in P naught. Okay. And it can handle a lot of heating also. That is what we see in general. Now we will look at the variation in gamma. Okay, I am saying blue is the most compressible, gamma is very low, and red is the least compressible. Okay, and gamma equal to 1.4 is our air sitting somewhere in the middle. Okay. So, if I look at my temperatures, I see that the most compressible gas can be heated a little more than the least compressible gas. Okay, it is the same here also, it is not very clear here, red is on the top, green in the middle and blue at the bottom, but the difference seems to be very low when it is subsonic curves. In supersonic there seems to be a clear difference, okay, that too only after 1.5. Okay. I was finding that when the gas is more compressible, it can handle a little more heating. Okay. So, it will not reach choking as early as the less compressible gas. It can get a little more compressed and try to squeeze through the gap available. That is the way to think about it. If it can squeeze through, that means it is more compressible, right. I just want you to get this physical feel so that you will never forget this. That is why I talk about squeezing through the same area and stuff. Okay. So, if it is more compressible, it is going to be able to handle a little higher heating levels. Okay. But the compromise for that is you are going to lose more on P naught. Okay. If it is more compressible, I am going to lose pressure energy a lot. It can handle a little more heating, but pressure energy is higher. I have to drop a lot more higher P naught if it is more compressible gas. This is properties of P naught and T naught variation. Now, we will go for pressure, temperature and density. Okay. Without even looking at the legend, you should be able to tell for fan of flow, the only curve that goes up and comes down is temperature. Okay. And what is the peak point there? 1 by square root of gamma. Okay. That is what you have to look at. And you can see that when gamma is decreasing, that number is going closer to 1. That is what is happening here. The peak is shifting towards that direction. Okay. 1 by square root of gamma. Now, we will look at details. If I look at any one of these curves, let us say I will pick pressure, the dashed line here. Pressure is coming very slowly changing towards m equal to 1, and remember that my flow always ends at m equal to 1 if I am heating the gas. If I am heating a subsonic gas, the pressure drops because it is accelerating towards m equal to 1. If I am heating a supersonic gas, the bottom one happens to be the dashed line and this one happens to be for density. It is supposed to be dash dot line. The dots are not very clear on screen. Anyways, this one is your pressure curve, and if I start with some higher Mach number and I heat the gas, it is going to go towards m equal to 1 and the pressure increases because Mach number drops. Okay, that is an easy way to remember it. Now, I will look at temperature. That is going to go do the same thing here, only in the subsonic side there will be a small change where I will now use density as my explanation. Okay. I am going to say now I will look at density, then I will come back to temperature. I will say this dash dot line, for low Mach numbers the change in density is high when I heat the gas. Okay. As I go towards m equal to 1, that is not as high, but it is still changing at m equal to 1. It is not slope 0 there. Okay. The change in density is very high for very low subsonic, okay, and pressure is not changing so much. So, what should happen now? T equal to rho RT, temperature should compensate for this change. The density drops a lot, temperature has to increase so that the pressure drop will be matched. That is why temperature is rising. Okay. And beyond a point, they all look the same and the temperature seems to flatten out at that point. Temperature need not change, pressure is same as density slope there. After some point, it will just change to the other way. Everything will go the way we expect things to go. Okay. Temperature should drop when Mach number increases. That is happening around this region. Okay. That is what you are seeing in here. The remaining things, gamma explanation, I believe you can explain. I gave this also as an exercise for fan of flow also. I will just leave this. I believe you can explain this very easily for compressible gas. Just leave that part to you guys. Okay. Now I will go to the next one, more interesting curve. I am now plotting the opposite of what I given as expression in your notes. I am plotting here S star minus S. If I plot S minus S star, that will go below, it is negative. Okay. Of course, if I am heating, I am thinking about this is the entropy change, S star is going to be the highest value and S will be lesser. Whatever expression I gave was S minus S star is higher than S, so it will be negative always. So I am plotting the negative of that so that it fits in the same axis. I did not want to put axis in negative also. Okay. So let us look at the solid lines, those are S star minus S. What this says is, if I am starting somewhere subsonic, I am going to drop in S star minus S. If I drop in S star minus S a lot, what does that mean? I am changing my entropy a lot in that region. Okay. When in here supersonic condition, that is not the case. S is almost equal to S star already compared to the subsonic situation. That is the way. Supersonic, subsonic case, the entropy change is higher than the supersonic case. Of course, now I will again say subsonic case it has only from 1 to 0, while supersonic case has from 1 to infinity all the way. Maybe that is why the curve is looking squeezed. Okay. We won't worry about that anymore here. But if I think about the compressibility effect here, if the gas is more compressible, and there is, ideally you do not know the answer to this really, if there is more possibilities of rearranging energy inside the gas, and so the entropy will increase more. That is the actual reason for this. Yeah, and this is out of scope of this course. If you want to deal with this, you have to go read high temperature gas dynamics or hypersonic flows. We won't worry about that in this course. Now we will go to the next one, Qmax. Okay. Qmax divided by, normalized by Cp temperature. Let us assume we start with the same temperature for the whole flow field case which I have plotted here, all same Mach, any Mach number, same temperature I start with, let us say. If I pick such a case, I am finding that subsonic case changes a lot. Okay. Qmax is high when I go far away from 1, much more than the supersonic case for the same amount. I will just go for say 0.5 and 1.5 if I look at it. Supersonic cannot handle as much heat as subsonic. That is the main point I wanted to say again. Okay. This is the reason why I will say, if there is a possibility of going through a shock, the flow can go from this point to a subsonic solution and still add a little more heat. There is a possibility of this flow doing that. Okay. And it may do that in depending on the settings. By the way, temperature is not the very important factor for determining the flow conditions in gas dynamics. We know that already. It is pressure and velocity direction. Those are the main boundary conditions. We will just keep this in mind. Now we will go and do a little more analysis. Okay. I want to now think about the fan of flow, or not fan of flow, Rayleigh flow in terms of TS diagram again, and just talk about it a little bit. We already had this kind of a curve for this TS diagram. We said that this particular point corresponds to m equal to 1 by square root gamma. This is my star condition, and this is my m greater than 1, m1 greater than 1, this is my m1 less than 1, and we said that if I am heating I am going to go this way, heating will go towards m equal to 1 from both directions, cooling will go the opposite arrow. That is what we found here. Okay. Now, what will happen if I have a shock somewhere sitting inside? Okay. If I have a shock sitting somewhere inside here in the supersonic section, then it is suddenly jumping from here onto some other point. Okay. And of course, I do not know the exact shock characteristic here, I do not know whether it is jumping to this point or to this point, I am just generally drawing a line here. It will jump from some supersonic point to a subsonic point. If it does that, after that it is going to go this way and reach m equal to 1. Okay. This is what will happen. Just remember this, that if I start with supersonic flow and I give some amount of heat, okay, I give some amount of heat, it can either go this way and go there, or it can go jump across with a normal shock and then go along this line to reach that value somewhere. If I put T naught star, then it will go and reach this point irrespective of whether it goes the subsonic path or the supersonic path. Then when will the flow choose to have a shock or not have a shock? Okay. Basically I am telling, if I give a heat addition from this point, say I started somewhere here, this is my M1, I am saying this is my M1, supersonic M1 I am having, from here I am going to add exactly the Qmax value, which means the final point should be this. And now I am saying I can either go straight along the supersonic path to this, or I can go this way, pick a normal shock in the middle and then go this way. I know that normal shock does not change T naught, right. So, it does not change any heating value or T naught value anywhere. So, it is going to have the same T naught whatever it was here, here also, from here it is going to choose this solution. Now, which one will my flow choose and why? That is the thing we need to think about a little bit. Once I understand this, now I can go proceed further into PV diagram. I already gave a clue just before starting this discussion. Okay. What is the main difference because of normal shock? T naught remains the same, P naught changes, stagnation pressure drops. Okay. So, it may so happen that I am having some other downstream boundary condition in my duct which is adding heat to the gas, such that the pressure may not be matching the downstream pressure. If such a thing happens, then there will be a shock forming to manage the P naught value such that it will meet the pressure value at the exit. Okay. That is how this shock forms in the middle. Okay. It has nothing to do with it is not similar to our fan of flow where we will tell the P naught drop should match the exit pressure exactly. Here again I am going to say the same thing, P naught drop should match the exit pressure, but our main problem is not P naught, it was T naught. T naught does not change anything, it does not decide the shock location here, can be anywhere from here to here. I could have another path that will be this, it could be this path also, it starts from here and jumps to this point and from there it goes to sonic condition. That might also be a possibility. Depending on whatever is the P naught required, it will choose whatever solution it wants. Okay. And by the way, if I have partial heating, I do not want to erase this picture, I will draw one more. And say I heated only up to this T naught value, that is P naught, right. Let us say this is my T naught star and currently I am sitting at this T naught 1, and let us say this is my S value, this is where I am currently, this is my T1, let us say that is my T1, I am sitting in supersonic condition and I am here. If I supply heat such that it is going to go end up only here, let us say this is my 2 T2 and T naught 2 will be slightly higher than that, this will be my P naught 2. while P01, this is my P1, P2 curve, and P02 curve will be, P01 curve will be sitting here. If I have some situation, I see that P01 decreases to a P02 curve has shifted to the right, that means pressure decreased. Okay. Now, yes, I am going from here to here. Oh, this curve is not right, right? Pressure should increase. I will draw the curve like this for pressure here, and this curve will go up like this. Pressure will increase a little bit to reach that point because Mach number decreased. It is going to go that way. Okay. Maybe I heated only up to this point, right? Instead of going all the way to T0 star, I heated only up to this point. This will have a particular P02. Okay. But let us say I apply a back pressure that is more than this P2. Okay. I give the same amount of heating, but I apply a higher back pressure than this. What should happen? Similar to nozzle flow problem or like friction in a duct problem, everywhere there will be some extra compression waves coming from the exit, because I will draw this, let us say this is P1, P exit equal to the current P2, okay, and but PB is greater than P exit. If I have such a case, what will happen? There will be compression waves coming inward, and as it comes inward, somewhere it will go form a shock which will become stable. By the way, I am assuming somewhere here that the heating is uniform along the length. It need not be. Okay, I am assuming that the heating is slow and uniform along the length. As it goes through the length, heating is also increasing. That is my assumption here. It need not be the case. Let us assume that for now. Okay, if I think about that kind of slow heating system, then I am going to say that there is going to be a shock that is coming in here, inside here, and sitting such that I am going to jump from here to some other value across a normal shock from some location here. Let us say this is S1, that is my just before the shock location, and this is my S2 just after shock location, and from here it is still going to reach the same T0, okay, but the P0 can change now, right. Of course, the P itself has changed. It can go sit somewhere else, and the pressure will now be this P2 prime, I will call it, or P2 with shock, P2S I will call this, same T0, and it will sit with this P0 to S. There is an extra P0 drop you can see because of that, because of the shock sitting here, and the pressure has now gone up to somewhere else. Okay, but it is still the same T0 line. I need not have heated all the way up to T0 star. Okay. I need not have heated all the way up to there. So, I can have two possibilities when I have supersonic incoming flow. I can go through just a full supersonic path all the way with the heat, the same amount of heat, or it can have a normal shock such that it will match the pressure and sit somewhere else out there. Okay. If I had some other pressure, let us say the pressure is such that it is lower pressure value, let us say it is between this and this, what will happen? I need a curve that is closer to this line. So, my shock will shift this way, okay. My shock will shift this way, so that it will go and do that there. That means I am basically saying my Mach number at which the shock happens will now decrease. You remember that here is high Mach number, there it is m equal to 1. My Mach number at which the shock happens decreases. Okay. All this you can just get from just thinking through the curves here. Okay. Of course, I am going a little fast, but just go and think through it, you will get familiar with this. We will come back to it when we go back to PV diagram for the same discussion. That again gives you a little more flavor to this problem. Okay. Now, we go start our PV discussion. Of course, PV is the set of variables which people use in thermodynamics, and in gas dynamics we typically use P and 1 by rho, which is same as specific volume anyway. Okay. But anyways, I will use small v cut as my specific volume. This is equal to 1 by rho, okay, and P. These are my two variables I am going to have for my plots. But before that I want to relate density and pressure so that I will know what plot I am going to have. This is not new to you, you have seen this in shock relations, it is going to be the same. Okay. But of course there will be some small difference. In shock there was no external heat added, now there will be external heat added, that will be the main difference. Okay. I will just recall that expression which we derived in shock just so you get oriented with what I am going to do, and then you will find that this is not the expression for our problem here. You may recall this expression, this particular expression is true for q equal to 0 case. Okay, this is a special case of what we are going to do derive now, and you will put q equal to 0 in that new derivation, you will get to this expression exactly. Okay. Now you want to start from scratch, I am going to say mass rho 1 u1 equal to rho 2 u2 equal to m dot by a, momentum, again I am doing the 1D derivations, not new to you. Okay. From here I can directly go P2 minus P1 by P1. Okay, I take it to this side and divide by P1, that is going to give me rho 1 u1 square by P1 into 1 minus rho 2 u2 square by rho 1 u1 square. I jumped a step in the middle, but you can easily see that. Okay. Now I am going to say I will use mass equation inside this. Till now this is only momentum equation rearranged. Now I will use mass equation inside here, rho 2 u2 equal to rho 1 u1. So I will cut off rho 2 u2 from here, only 1 u2 will remain, 1 u1 will remain. So I am going to write this as rho 1 u1 square by P1 into 1 minus u2 by u1. Okay. Now of course we have been doing this a lot, this particular term will directly become gamma m1 square. Okay, we have been doing this the last few days, a lot of it. Okay, you can directly see P by rho is RT, and then you multiply and divide by gamma, you get to that expression. Okay. So now u2 by u1 from mass equation, u2 by u1 is rho 1 by rho 2. But from our V equal to 1 by rho, I can rewrite this as u2 by u1 is equal to V2 by V1, where V is my specific volume. So I will now write my expression as P2 by P1 equal to, I am taking this minus 1 to the other side, 1 minus gamma m1 square times V2 by V1 minus 1. I will end up with this particular expression, and I will just rearrange the terms so that I will directly talk about P2 and V2 relation. 1 plus gamma m1 square minus gamma m1 square times V2 by V1. Okay. What we are seeing here is this expression I got from mass equation and momentum equation. Okay. By the way, this is the same thing as what I did for shocks, I just written it in a different form. This is your Rayleigh line, okay, in your shocks. I do not know whether I gave it as Rayleigh line, but now I will call this the Rayleigh line. Okay. This is conserving mass and momentum. Okay. That is all this particular expression is conserving. What I am seeing here is, for my flow we know mass and momentum are conserved, which means P2 and V2 are related this way, they are linearly related, right, and they are inversely related, minus 1, not inversely related, minus V2, P2 is proportional to minus V2. So I am going to have a negative slope. Okay, if I draw a P2 and V2 curve. Okay. So if I draw my PV diagram, I will draw it as P2 by P1 and V2 by V1. Okay, I am normalizing with some particular value the initial pressure, and let us say this is my 1 and 1, which is the starting point P1 V1, that particular line. From here I am going to go to some curve like this. Okay. That particular curve corresponds to one of these m1 values, some m1 value, that is all it is going to be. Okay. You will end up with that. Okay. And we know that it has to satisfy 1 and 1 always, because if I substitute P2 by P1 equal to 1, then this term should cancel this term, that will make it V2 by V1 equal to 1. Okay. So, 1 and 1 are always satisfied, even though it looks as if the intercept keeps changing with m1, it is changing such that it will match this particular point always. Okay. If I have another Mach number, it is going to be like this. Which one is higher Mach number? I have to label them first. A and B, they are all straight lines. I have A and B, which one is higher Mach number? The slope is what matters here. The slope magnitude is gamma m square. Okay, both are negative slope. The slope is gamma m square. If m is higher, then it will have higher magnitude, it will be more vertical. Okay. So, I will replace this, B will be higher Mach number. So, I will replace this with the curve, this thing saying m increasing this way, and here m increasing this way. Okay, when I go this way, m is increasing. It is as if I am having a straight line and I am rotating it about this point. As m increases, it is going to go more like this. Okay. Just remember this is just our Rayleigh line and how it works. Now, still I have not used our ideal gas law, energy equation, etc. Okay. Now, we will start from wherever we are currently and add energy equation to this. If I add energy equation, now it is going to be U2 square by 2 plus CPT2 is equal to U1 square by 2 plus CPT1 plus my Q, where Q is my new addition compared to my shock case. Okay, this is the only difference. Okay. Now, because of this, of course, my expression is going to have Q in every term. So, now if I make Q equal to 0, I should get back to my normal shocks as of now. Okay, we will keep it that way. We will substitute Cp in terms of gamma and R, gamma minus 1 by gamma R by gamma minus 1, that will be my Cp, and I want to rearrange this term U2 square minus U1 square. Okay. Of course, I could have a divided by 2, I will just take the other things and multiply them by 2, okay, is equal to 2 times Cp's are together. So, I am going to take gamma by gamma minus 1 times R, okay, times T1 minus T2 plus Q. Okay. The Q should also have a plus 2. 2 is multiplying all the terms, 2 is there also. Okay. Now, of course, this can be now rewritten RT together. Okay. RT1 can be written as P1 by rho 1 and RT2 can be written as P2 by rho 2. Okay. So, I can write this as 2 gamma by gamma minus 1 times P1 by rho 1 minus P2 by rho 2 plus 2Q. This is my U1 square minus U2 square. Okay. Now, I will just take one expression from our normal shock derivation. From mass equation and momentum equation, it can be shown that U2 square minus U1 square is also equal to P1 minus P2 times 1 by rho 1 plus 1 by rho 2. Okay, I am just taking this, otherwise I have to write 3 more lines. I just want to take this from normal shock relations. We derived this exact equation when we were doing normal shock relations. Okay. So, now I want to link this with this relation, because both are u2 square minus u1 square. Okay. I want to equate these two right hand sides, and I will write 1 by rho as my specific volume now. So, my expression becomes P1 V1 minus P2 V2 times 2 gamma by gamma minus 1 plus 2q plus P2 minus P1 times V1 plus V2. This whole thing is equal to 0. Okay, I just rearrange these terms so that it looks like this. Okay. So, now from here I will group the terms such that I will have P2 V2 terms together. Okay, I have P2 V2 here, I have P2 V2 here. Similarly, P1 V1 here, P1 V1 here, and of course I also have P2 V1 and P1 V2. We will leave those out for now. Okay, we will group all the terms in a nice way. P2 V2 times 1 minus 2 gamma by gamma minus 1 plus P1 V1 times 2 gamma by gamma minus 1 minus 1 plus 2q plus P2 V1 minus P1 V2 equal to 0. Now, of course, this will become gamma plus 1 by gamma minus 1. This will be minus of gamma plus 1 by gamma minus 1, and the other terms are just simple. Okay. So, this expression, if you look at it, this is P2 V2. I am going to say P1 and V1 are fixed numbers for my flow. I just want to see what are the relation of the exit P and V, P2 V2 product of these two, and here it is just P2 multiplied by a constant, V2 multiplied by a constant. So, overall this is an expression for a hyperbola. Okay. Overall it is an expression for a hyperbola. If I do not have this, it is a rectangular hyperbola. If I have this, it is a slightly tilted rectangular hyperbola. Okay, that is what you will get. Okay, I hope you know some amount of geometry to understand that. If not, just go and draw the figure, you will anyway see it. I have the plots anyway, I will show it to you after I finish these derivations. Okay. So, if I rearrange this, I just want to go back to the original thing I wrote there. If I rearrange this, I can get it to I will get to this expression. Okay. From here, now I can get P2 by P1. Okay, I will just divide the whole expression by this value and P1, this whole bracket and P1 I am dividing. So, I will get P2 by P1 as V1 into gamma plus 1 by gamma minus 1 minus V2 divided by this whole expression V2 times gamma plus 1 by gamma minus 1 minus V1 plus 2q divided by P1. I will write this first. I will put it as 2q by P1 as a separate thing, multiplied by this. Okay. It comes to this expression. Now, if you look at this, I can divide the numerator and denominator by V1, okay, sorry V2, so that I will get back to the original expression I had out here. For q equal to 0, I will get to this expression finally, okay, because rho 2 by rho 1 is equal to V1 by V2. Okay. This will become V1 by V2. So, I just have to divide this expression here, numerator and denominator, by V2, then I will get to that exact relation there for q equal to 0 case. Okay. So, this is a superset of the previous expression we had for normal shocks. Okay. Now, of course, the only thing remaining is I have to know the functional form of this. Okay. Again I am going to say 1 and 1. There is some starting point. First I will draw a curve for q equal to 0. I said it is a rectangular hyperbola with the axis tilted slightly. So, it is going to look something like this. Okay, this is for q equal to 0, that is no heat added. Okay. Now, if I add any amount of heat, if I have a q, then from this expression you can directly see that if q is positive, immediately this expression is going to have a higher value. Okay, it is going to have a higher value for the same V2. P2 will be higher for the same V2. So, if I look at that, the curve is going to be above this curve. Q will be, for q greater than 0, it is going to be like this, and if q is less than 0, that is I am cooling, that will be like this. Okay. These are your curves, this is how it will be. Okay. Now, if I want to find what is my final state P2 V2, this particular curve, set of curves will satisfy mass, momentum, energy, state, okay, and the previous one will satisfy mass, energy and state for this one, and mass, momentum, energy for the Rayleigh line. From here I will draw the Rayleigh line also, say for a particular M1. For a particular M1 if I start with, it is going to be some curve like this. So, my final solution has to be an intersection of these. Okay. I have drawn it such that it is almost tangential to this particular curve. So, it can only be cooled, it says. Heating does not give me solution, that is what I have. If I draw another slope for my Rayleigh line, let us say I will pick a very low slope, that is my Mach number is very, very small, then I will have something like this. I may be cutting at several points here. I find that if my Mach number is very, very small, then if I cool it, I can have a solution there where pressure increases, which you know is our going more subsonic, pressure will increase, that is this solution. Or I can heat it and go to a solution where my pressure decreases a little bit, okay. That is I am having a higher Mach number and it goes to this particular point. Okay. It so happens that there are two solutions, and I will just tell you directly here that this particular solution delta S is less than 0. I can prove it to you, but just ignore that point for now. Okay. We will prove it to you some other time. Okay. Delta S is less than 0 if I have to go there. It is going to tell me that I start from subsonic condition and it is going to end up supersonic just by heating. Okay. That is not possible, that is not allowed by entropy anyway. Okay. So, it is going to be only this. Now, if I consider a very high Mach number, that is supersonic Mach number, this will give me this kind of a curve. I am drawing too many curves here, I will go back to plots with colors later. Okay. I call this curve as 1, this Rayleigh line as my 2 and this Rayleigh line as my 3. If I have this, and if I do not heat, of course, oh I did not talk about do not heat at all. If I do not heat, of course there is a solution of P2 V2 equal to P1 V1, that is a trivial solution always, that is always a solution. Okay. And there is no other solution for one other than cooling. Okay, that is a special case. We will come back to that special case when I discuss it with the figure on the screen, but currently we will just look at this. And if I go to high Mach number case, if I cool the gas, I am going to get lower pressure, that is I am going to even higher Mach number, that is this solution. And you can see that the volume increases, that means my density dropped. Okay, I am expanding further to higher Mach number, that is this particular solution. When I go the other side, this particular line, if I go from here and heat it, oh I drew the Q such that it never touched it. Okay. Maybe I have to go to my plots, okay, and I will do the plots thing next class because it looks like the time is not enough. You will find that there are two solutions probably possible, okay, or just one solution depending on the situation. Okay. That particular plot we will discuss next class because there is a lot of information hidden in them. After that we will go solve some numerical examples and we will close discussion on heat addition in supersonic diagrams. Okay. After that, I will just give you a brief idea of what if everything is present: heat addition, mass addition, friction, and area change. Okay. Just probably one class of that, and then I will move on to some other sections, experimental methods and method of characteristics. Those are left. We will go for that after that. Any other questions? See you people next class.